to active learning, and what do you see the potential of active learning being in the field, but most importantly for your own field and your own work? Kim, you haven't actually given your talk yet, but if you want to start, just press the mic on the other side. Is the press the button? Yeah.
Hello, is that working?
Yeah.
Yeah. Yeah. So hello, I'm talking this afternoon, so you'll know what I do then. But my name's Kim Jelson. I'm based at Imperial College London in the UK. So my background is more in computational chemistry, computational materials chemistry. Obviously, like many people have moved into using a lot of AI where it can be useful. And in particular, I've also worked very closely with experimental groups. I did postdoc within an experimental group that actually has quite a lot of representation here in the posters as well. And I guess generally what I talk about in the panel is at Imperial and within the chemistry department where I am, we have now an institute called DigiFab, or for Digital Molecular Design and Fabrication, where we're trying to sort of bring together and boost people's ability to work in this area. We have several automation facilities that people can access. So many more people are thinking about being able to do things like active learning. And we're quite interested in how we can sort of change the education so that we're giving everyone the skills to be able to do this, including experimental researchers. So we have added this in slightly to our undergraduate. Everyone learns to code in Python in the first term of their chemistry degree, which at least when I was an undergraduate wasn't usual, but also doing data analytics. And we have a one-year master's course that we launched 2 years ago called Digital Chemistry, where people get training in both the automation side and the machine learning and AI side as well. So yeah, I just thought I'd mention that aspect of it. And obviously also with DigiFab, we're thinking about a lot of the problems and hurdles you need to overcome in terms of data, software infrastructure, and having software engineers as well.
Okay, thank you. Adam?
Hi, yeah, I will be briefer, I guess, since you just already had to suffer me for a while. Maybe more on why we got into it. I think already from the beginning, we had a strong interaction with experimental groups. I'm definitely coming from the computational physics, atomistic modeling approach. And at some point, the sort of challenges we were facing could not be solved with the conventional approaches. I think already in 2014, 15, we started to look at genetic algorithm approaches, linking our simulations to virtual models into the experimental data. And I think this is just expanded there. And we see lots of routes now with the active learning to sort of dynamically do simulations with experimentalists. And I find this really exciting approach. And I hope breakthrough in terms of what we can achieve.
Yuri?
Thank you. So my name is Yuri, and I'm from Ruhr University Bochum, ICOMS, and my field of interest is data-driven method for atomistic simulations, and our main activity now is dedicated to developing interatomic potential based on new type of descriptors, atomic cluster expansions. Like my statement, I would say would be regarding the application of ML models in general, and it's like a common knowledge they are very good at interpolation, but they could be spectacularly failure at extrapolation regimes. And in that case, we need to have some, let's say, safe failure mechanism to prevent that, or at least to signalize. That's why active learning based on uncertainty indication came naturally. So that's why we really like looking forward to adopt this. We're already doing this and have it implemented to adopt this uncertainty indication methods for atomistic simulation. And I believe that like in a not so distant and bright future of interatomic models and simulations, that became like an industrial standard to have uncertainties of your models, like experiment has error bars, why simulation should not have it. Thank you.
Yeah, so hi everyone. My name is Rasmus Grunberg. I work as a computational chemistry specialist at CSC, which is the company providing the HPC infrastructure and services in Finland. And I have a background in DFT-MD simulations, looking at solid liquid interfaces, and I've been doing some machine learning also at the side, but that has not been sort of a main focus. But nonetheless, I think the sort of importance of machine learning and artificial intelligence, active learning, is undisputable, and I think it's really important to stop and think when you're doing computations that you're computing smart and not hard. So I mean, even though we have huge supercomputers and nice HPC infrastructure available, it's really important that we try to utilize those resources also as efficiently as possible. And I mean, initially, before the sort of machine learning boom, so to speak, enhanced sampling techniques within molecular dynamics have sort of enabled us to do a lot much more efficiently compared to just running brute force MD simulations. And similarly, I think the sort of advent of the large variety of different kinds of machine learning techniques will allow us to achieve results much more efficiently, much more faster, with much less power consumption, smaller carbon footprint. And I mean, these are also things that we need to consider, because the computational power it's not free. So I mean, this is really important, and the presentations we've seen now here have really shown sort of great promise, and I'm really excited for the developments that are coming.
Okay, thank you. Do we have now questions from the audience, either remote or in person? So while you ponder this, I know you've only just had coffee. I'll continue. So I was wondering if you could comment on sort of the opportunities of generating data with active learning, which is a different paradigm to, you know, pre-computing or pre-measuring data sets and then applying machine learning to that. So we have three very different application domains, right? We have CSC as a provider of resources, then atomistic applications, and then to experimental applications. So maybe Rasmus, if you could start saying what you see in this, do you see it as a paradigm change, and what challenges is CSC facing when data is generated with active learning workflows?
Yeah, so I mean, of course, looking at sort of more technical side of it, I mean, of course, the generated data to augment the available data that we have is really sort of an interesting sort of topic, and of course, but then if you look at the technical issues that we are facing, perhaps more in general as well, when we are dealing with large data sets and reading and writing lots of data. So how to do that as efficiently as possible, so that these kind of workflows are different from the sort of traditional HPC simulations that we have, and this puts some restraints, for example, on the sort of parallel file systems that we have on the supercomputers, and how you do this sort of dealing with the data and the input-output operations is of course something that one needs to take into account. But for sure, I think this is a really interesting avenue and will open up new possibilities.
Thank you. So from the point of view of interatomic potential generation and parameterization, I think that generating data based totally on, let's say, uncertainty indication is not 100% reliable, I would say, because we still need some, let's say, domain expertise of potential developer to really kind of guide and direct this mechanism towards certain applications. So for example, either you're interested in the bulk defects, or you're interested in open surfaces, or you're interested in, I don't know, molecular dynamics and gas phases. And in that case, I would say that the ideal case scenario would be a combination of both man and artificial intelligence, if you can call it like that. That would be like a co-pilot in order to generate and guide the search and create a new data for updating the models that would be like directed by humans. So I would say it's would not replace 100% the main activity, but it will greatly enhance it.
Yeah, I guess for us, we are very interested in getting experimental data because it's so rich, but we're facing a huge challenge in it's sort of the two barriers I see. First of all, is convincing experimentalists to spend extra time, you know, because they can just measure and publish, measure, publish. It's great. It's a great model. Measure, curate your data, store it, label it. And I do understand their problem, even if I just talk, I mean, it's a real niche field, and of course, machine learning and scanning probe microscopy, it's like niche within niche within niche. But even within AFM, there is so many different prototypes. There is like a different interface needed for every single instrument. And, you know, this is what we're facing. And our challenge then is we have to say, they say, yeah, we'll give you the data, write us an interface. And this, we are willing to do this. But I think there is this communication error, that persuading people to get involved, make that step, that effort, and try and make it as easy as possible from our side.
Yeah, so I think, like Adam, where I really find it interesting in terms of using things like active learning is when you're working directly with experimental groups and actually in scenarios where we don't start with a lot of data. So where we have a low data situation, because one way in which we use machine learning and generally a lot is where we already do have thousands of data points, and then we can just do something more along the lines of supervised machine learning. And you have scenarios where you can do that and where you can generate a lot of data either experimentally or computationally or from existing databases. But much like Adam, but in a different perspective, one of the reasons as a computational chemist that I sort of gave in to a certain extent and started using lots of machine learning is this point that the data is much richer. It includes all this complexity of things that as a computational chemist, I was always trying to avoid having to consider, like solvent and things like that intrinsically. I have a good fortune of having a particularly good experimental collaborator that uses a lot of automation equipment, and therefore we have this great opportunity to use things like active learning, where you start with a low amount of data, but now we're like much more cleverly collecting the data as a more efficient way to search the space and to try to find optimal materials. So that's where I think it's quite exciting, but you've got lots of challenges in terms of thinking about your data infrastructure and how you're going to have the flow of data transfer and so on.
And in particular, when it comes to the experimental data, we also have some experience with it. And there, the paradigm is really different in active learning from previous machine learning, right? And I was wondering if you could comment on this. It helps with reducing the amount of data you have to collect because you're collecting in a smart way, but then you're introducing a huge amount of bias. So this is okay if you're trying to optimize, right? Or you're looking for something in particular and you're getting there faster. But then often there's the desire to use the data later for some further machine learning, but then you've introduced the bias. So I think the community might be unsure how to handle such data sets. So I'm wondering if you have an opinion on that. And this also, I think, goes for the data that is generated in potential training. Could it be made available later as data sets the way we know data sets right now? Because a lot of machine learning, in particular in chemistry, has been advanced because data sets were available that you could train on. But if we now make these actively learned data sets available, do we have to be extra cautious?
Yeah, I mean, it's an interesting question, but again, you're at this point where the experiments would say, brilliant, you've done this active learning. So I've got my spectra of the thing that interests me, and now I can understand the science. And to say to them afterwards, yeah, but is this bias? I mean, isn't the question then the only way we could handle this is in the data storage? You actually have the entire history of how this data was. So, you know, that if you use it later, all the metadata tells you, okay, this was done in this way with this active learning bias. And we're smart enough, we're very arrogant. We're smart enough that we can understand how that might have affected our, you know, again, it's hammering the drum that I know Patrick also agrees with. This, you know, managing data seems to be a big issue.
Thank you. Regarding the data sharing, I think it's not a new problem, and nowadays it's quite common when you publish some research on atomistic simulation, for example, using ML potential, especially if you develop by yourself. Usually you're required to provide in one or another way the data set. A new problem that could appear, and it's already, I mean, we face it a few times. If you, for example, want to continue develop some other published potentials using the data set, and you can use it as an initial guess for your active learning scheme, question of reproducibility and extendability of calculations. Maybe that was computed with some old version of, I don't know, quantum express or WASP, and maybe the settings was not full enough, and you not able to generate consistent or continue to generate and extend this data set in a consistent way. So reproducibility became really important if you want to adopt this active learning extension of the data sets.
Yeah, one thing to add also here, I think I agree completely, and in addition to making the data reproducible and sharing the data, I think the whole workflow should be made reproducible, and I mean there are lots of effort to make these sort of common workflow languages and how you can set up your workflow in such a way that it's maximally reproducible and easily shared and adopted by anyone else. So this is also a very important thing to develop, I think.
Kim, did you want to add?
Yeah, I think it's an interesting question. I mean, one thing though, if you're fully sort of exploiting all the tools you have with machine learning is, I think, as it was in Antonio's talk yesterday, he could sort of really plot and look at where have we sampled previously. So you can also use some of these techniques and clustering, etc., to try to identify new regions to go to. Because what I'd say in terms of data bias is, if you're not doing it via this type of approach, you've also got enormous bias. In fact, at least in my area, you're basically just looking at the things that would have been easiest for someone to experimentally make, which is a very niche area, you could say, of the potential chemical space you could have gone to. And I guess I would just touch back on the point that I mentioned when I introduced myself about educating all chemists as part of their early undergraduate, etc., training about data analytics and these techniques, so that even when they're experimental researchers, they have that aspect of it in their minds. So that will encourage them to be using electronic lab notebooks, but also to see the opportunities from a data perspective. And therefore, I guess I have more hope from that perspective as well, like new generations of chemists that are just doing sort of good data practices and so on from the start. But yeah.
Okay, we have a question from the audience, or several. Melissa. This is Andre.
Sorry, did you want to also ask a question? Oh, everybody who wants to ask a question, please raise your hand like this, otherwise we don't see you. So yeah. Okay.
So we've had some really fantastic talks here, but we've really heard the power of machine learning, and I might be saying it's about to take over the world. And so I was wondering if you could say a few words, please, about sort of what can us mere humans still contribute?
We have to write the funding proposals. So far. Yeah, I don't know. The thing that jumps in my mind is immediately this education is, you know, okay, I'm joking aside, of course, we're still needing all these machine learning processes. This validation is always us. And every time I think we get a process fully automated, that's great. Let's move on. New science, new physics, something more complicated. There's always something new to do. So let's make the boring things automated and get the new things that machine learning is telling us where to look. That's the essence of active learning. Let's apply our brains there. But then I think this education this is super critical. I think, you know, Patrick has been pioneering here as well with getting machine learning into the material science communities. This changes things. And I still think we are better at teaching machine learning than machine learning. But some might disagree.
Any other comments? I mean, we don't have to go through the whole panel. Okay. Yeah, Kim, if you want to
No,
add.
it's very interesting. Posters also on the idea of human in the loop, and that's Tonya was mentioning a bit of that as well tomorrow. So it's about smartly having workflows that use AI and then the human brain where each of them is best.
Yeah, and spoiler, we'll hear more about human in the loop tomorrow in the first invited talk. Andre, you had a question?
Yes, I have a question about kind of how to, sorry, now I've forgotten the word that I was looking for, how to connect things going on, sorry, how to unify things. For example, starting from my point of view from right to left. So we have now 3 or 4 languages for GPUs. So is there some way the machine learning could help us? Like we will write what we will want to do, the code, and it will automatically tell us everything. Then to Yuri, for example, at the machine learning force field, whatever it is, if there will be in the future or common future, nearby future, something like universal force field. We know that universal force field in MD is really bad, but it's there and it can do almost everything. Or will be there some, classifier, I have this kind of problem, this elements, this interactions are the most important. Which force field, which already learned machine learned force field would be the best for my problem? And maybe go on like the unification within around different machines and the standards within experiments and so on. I cannot comment on all of this, so please, thank you.
Yeah, that's really interesting. I would say that, so as far as I'm aware, if we look at this, for example, GitHub Copilot and these kind of sort of helpers to do programming and maybe port applications then to different, let's say we have some software that is programmed with CUDA and then to be run on NVIDIA GPUs, and we would like to have a machine learning algorithm that translates that to HIP to be run on AMD GPUs. I mean, this is probably something that could even be done at least to some extent. So I see a potential there to at least get a good initial starting point, and then you can of course have the human there validating that does this make sense. And sort of my impression is that, for example, GitHub Copilot is that's really good for sort of writing boilerplate code and sort of helping you to do boring stuff, but then sort of really coming up with nice algorithms and something that's really something new and efficient that doesn't really work yet. But for sure, I see a great potential there to have machine learning algorithms helping you to, for example, design your model parameters, picking good good parameters for doing a simulation for a certain type of system, and even then doing some porting of code from a language to another. Yeah, for sure.
Thank you. So so you had several questions. I tried to answer most of them. So first one is regarding like universal force fields and so on. For the moment, I'm pretty skeptical about this because the complexity of that, you will just restore the complexity of DFT back again, maybe with some small gain, right? And regarding the, different type of models, or for example, one approach, neural network, gap solve descriptor, ACE, whatever. Just let's take a back look into history. For example, which DFT code you're gonna use for your next project? How many DFT codes do we have? And that's already for like several decades, and it's the same. So people just change depending on the application. One code is good for something one domain, and another for another, and you just choose the right tool. Maybe in order to develop this thought a little bit more regarding the man in the loop and how we should just live together with ML, just remember industrialization and switching from manufacturing to automation of hand labor. Now we're switching from towards automation of mental labor in one way, but of course that brings some disturbance into job market. But that's how it is. That's just part of evolution as a mankind, I would say. And it's we have to adapt and go on. So I would say there would not be single best bullet, silver bullet for all the problems, but there is a majority of them. We just have to learn how to use it. maybe several times during our career. Maybe in the next 20 years, we get quantum machine learning and we don't need any GPU anymore. We will do all on the spin qubit systems and so on. Just be ready to learn new things several times during your life. Thank you.
Do you know if there's anything you want to add, Adam and Kim?
I think this is enough.
Okay. Matthew, you had a question?
Yeah, hi, thanks. I hope you can understand my voice today, but you know, data management has been something you discussed in the first few points there. And I guess with the completely sort of exponential growth of machine learning and science as a field, how do we sort of accelerate our data management or improve our data management at that same rate, so we don't just end up in a mess of everyone using different solutions and completely not interoperable solutions? So what kind of social model, I guess, will scale our data management at the same rate as machine learning?
Maybe Kim and Adam can start and then hand over to Rasmus, who runs the biggest database in Finland.
I mean, I think this is a huge challenge, and the only way we can address it is from all directions. So yeah, there is like great efforts across Europe and the States of introducing data management and advertising it and selling it. But now we're increasingly seeing it coming from first the journals, or maybe at the same time the journals, that they are pushing back and saying, I mean, especially I think in bioscience, things like this, we want to see your data, we need to see the source files. So this is coming. So even if you're skeptical or lazy about getting involved in the process, when the journal says we're not accepting your Nature paper until you give us all your raw data, people tend to get motivated. And I think at least in Germany, maybe the funding bodies are demanding this. I mean, Finland is the same. And I think this is a good way that it goes. I mean, eventually this will become, I mean, it already is becoming legally insisted upon in certain countries, but legal frameworks in the EU, certain countries leave, etc. You cannot rely on this. Sorry, Matthew. So I think all fronts, because it's critical. It's a critical problem.
Kim, do you want to add to this?
Yeah, I mean, I think Adam's answered that well, and it is that part of the problem is that there is no one solution that's going to fit everything. At least in chemistry in my department, from the experimental perspective, we've moved to mandating electronic lab notebooks for all PhD students that are doing any of our streams to do a digital chemistry, but they can also be a bit restrictive and actually not necessarily the work the best for us as the computational chemists doing the machine learning. So I think that still needs to evolve, and we're thinking a lot about strategies for that in our department and across our facilities now, where we've got the automation facilities that are going to generate lots of data and how to do what we can to future-proof it. But I think it's an interesting, like the sort of sociological type or whatever problem in terms of trying to shift the expectations. I think in our field we're lucky, and I'm sure when we review papers, I'm sure everyone here is generally quite insistent that the research is coming along with the associated data and raw code and so on. But we probably recognise that we're at the moment, at one end of a spectrum. So I think there's a lot to do in changing the way they work. Again, I think there's a lot of promise for the future, and that the younger generations just want to do that already. They don't need convincing. But yeah, I think sort of flexible solutions are needed. And I think we also need to remember, and what often doesn't come along with facilities, is the necessary people, the software engineers and so on, that we need in place with long-term contracts and very highly skilled software engineers, but that also understand your field's problems, whether it's chemistry or material science as well. And yeah, there's certainly schemes in the UK, but interesting sort of funding schemes coming now are saying that they'll come with a lot of software engineering being allowed to be costed in that would be long term. So I think for me that's quite exciting, because I think we need that. We can't expect the researchers to be solving these problems on the scale that's needed.
Rasmus?
Yeah, I mean, to add here still, so I'd say that in addition to having policies and mandating that the data is made public and stored following FAIR principles, we really need to have also functioning solutions for doing this as easily as possible. So I mean, this is yet another step for the individual researcher to take care of the data, that it's stored and accessible and reproducible, but really this should be also as easy as possible to sort of, because I mean, you guys doing research, you have, I mean, your time is needed somewhere else than just like, I mean, I'm not saying that data management is not important, but it should be as easy as possible, and sort of the extra time you spend on that should be as minimal as possible. So, I mean, and this is also where the software engineers and having these people available who can implement and maintain these systems that allow uploading data, writing metadata, and storing. I mean, ideally, we would have some systems that allow you to you have your simulation that you run on your local supercomputer, and for example, you have just one liner in your batch script that then submits the data, writes some metadata to it to some object storage service or somewhere else. So really implementing these kind of solutions and having repositories like Nomad and these kind of things. So keeping those up is really important, and developing the usability of those.
Okay, thank you. Rensel, you had a question?
So my question is, my issue with
Please turn on the mic.
Okay.
And speak into it.
It's on. I'm sorry. So my issue with machine learning is that it can't. My understanding is that it can't bring new physics into the picture. So if my training set was just say DFT calculations, I don't see how it could come up with BCS theory like Cooper pairs or high superconductivity. So for me, machine learning is just it makes it more efficient with all the theory that we know. But can it bring new physics into it? Like in the future, with machine learning, could we come up with a theory for high superconductivity, for an example? Is that realistic?
Okay, I don't know if this panel is in the best position to answer the question, but let's give it a try.
Okay, since I got the mic, I will go first. So regarding the high temperature superconductivity, I'm not sure, but I would like to maybe bring another example. It's about the emergency principle. So do you know the game of life? I mean, it's just simple set of rules, which, I mean, it's as simple as 2 or 3 lines. It's describe behavior of some switch on, switch off positions of some pixels or active cells and so on. And, but despite of its simplicity, you can build really complicated things following these simple rules. And that's the illustration of emergency principle. Once you have some simple behavior, but it's robust, you can discover something new. So complexity increase. Now, if we go to, for example, atomistic simulations, once you have some learned rules of interacting of atoms in some local atomic environment with a limited cutoff, but still you can build some type of simulations, I don't know, large scale, long time, and so on, and learn some new physics because of this emergency principle. It will appear from the simple interaction rules. So I would say partially yes.
Anything to add?
Yeah, I mean, I would say, I mean, this is not something we strongly work in, but people really are, and they've rediscovered old theories. There is papers in the last few years where they have applied this and found some old, Hooke's law or things like this. So I don't think it excludes it. I think this is an active area of research that you can find physical theories. But again, it's about how you train. I agree. I don't think you're going to find it training on DFT data if the physics is not there, but you wouldn't do that. So you would look at something else. So I think there is hope, and we can be involved.
Okay, Kunal, you had a question?
Yeah, so my question is around active learning for data sets, right? So all this while we train our machine learning models on data sets which existed in the past, and somebody created those data sets with something in mind, right? So either they were just collecting huge chemical spaces arbitrarily, or doing some combinatorial search and stuff like that. So now we have these data sets. Now, but as we move forward with active learning, we are always optimizing for some property. So either mean absolute error for homo energies or force fields or whatever. And then we get some other data sets out of it. Do you think, and which might or might not be very useful for the tasks, let's say, later on. Do you have some thoughts around what we should be optimizing for compiling meaningful data sets for, I don't know, general science.
Okay, I also try to answer first, but everybody also welcome to join. I think that at least a practical approach that we try to adopt, that you can have like a core data set, for example, for interatomic potentials, that capture basic structures with a known high symmetry and some like extreme regimes like strong compression or dissociation limit and so on, just to stabilize the model somewhere. And once you have this backbone of your data set, which you can generate using, I don't know, just one button click approach, you can now, using your domain knowledge and intuition, so reference back to man in the loop, you can grow this data set to some applications that you're interested in now, right? And that would be just like a good initial starting point. Maybe, yes, with developing more and more experience and examples of using particular type of ML models and data sets, yes, we can extend our default backbone data sets in image recognition. So there is ImageNet data set of 1 million images and 100, I think, 1,000 classifications. And then people start from this, not even the data set, but pre-trained models to adopt to some particular computer vision problem. And that's the transfer learning. So I think that's the same idea. So you have something core, and after that you adopt and fine tune it to particular application.
Okay, thank you. We're coming to the end of the panel discussion. I don't see any further questions, nothing online. So I was wondering if each of you could maybe sum up and look a bit into the future and maybe address or raise one point where you think active learning could really contribute even more strongly in the future, or maybe one particular challenge of active learning that deserves attention and needs to be solved so that we can move forward. We didn't talk much about challenges. Maybe you can raise one challenge that you think is impeding progress right now.
So I would, if I broaden a bit to my impression about machine learning and artificial intelligence in general, I think it's really important that, I mean, as what Kunal just brought up, so really sort of paying attention to the data as well. So really, and also a bit regarding the generated data. So important somehow have the human in the loop to validate and make sure that there's some sort of a mechanism for really being sure that the models that we are developing are somehow reliable. And also I think extending even beyond material science, I think in general the sort of interpretability and explainability of machine learning models is really something that one should be paying attention to. So I see that there is a sort of slight danger in using blindly this kind of black box machine learning models without questioning them at all, that why they are making the predictions that they are making. So really sort of having some sort of understanding that is this prediction, for example, is it ethical? What kind of bias do we have in the data set? And developing methods to actually getting access and interrogating the model, that what is the reason it is making this prediction, and maybe even understand then something about the underlying physics is one important challenge that I'm personally at least quite interested in.
Yuri.
So I totally agree with Rasmus, and maybe it's interpretability of big ML models, like with millions of parameters and neural network of such a size is a long-standing and not new problem, but at least as a midterm, I would say that we need to adapt uncertainties of prediction, like in experiments. I mean, you probably could not publish so many experimental results if you do not provide an error bars on your measured point, especially if that's the main results of your paper. So I think we have to adopt for all or majority of publications involved ML models, please provide uncertainties of your model at least to increase the belief of community to this. Yeah, thank you.
Adam, any particular challenge in reinforcement learning?
Well, I was going to say more generally, you talked about active learning and the same for reinforcement learning. And I think this is, for us, is the challenge, is the cultural change in the experimental environment. I mean, I think we see in this meeting that people are really embracing it, but there's clearly fantastic experimental groups that are still not really seeing the benefit. And that's on us to convince them, you know. So I think that is the challenge, that why should you let the theorists control their machine even for 10 minutes? So this is what I hope we can prove with these. And it works. Every time we do a simple example, they go, okay, I can see the potential. So I look forward to this.
Kim?
Yeah, I think people have really covered most of the points I talk about. Like, I think the explainability is really important. I think also just to have the joy to doing these sort of things for us as scientists, you want to have that understanding, and the uncertainty prediction. And the uncertainty prediction as well. So the joy from explainability is what I just said. And I think the ethics point is interesting. We teach a bit of AI ethics to our master's students as well, and thinking how this might change how we work as chemists in the future, and in the industry as well is important. But I think Adam then covered really what I was going to say most. This cultural change, I think, is interesting, because where I'd say with active learning, I think there is everything there for it to be already used much, much more in chemistry. And to me, when I think of my colleagues in the chemistry department doing synthetic sort of organic chemistry, etc., they could all be using things for reaction optimization already. And where they've been involved in some of our teaching, they've said to the students, oh yeah, this sort of Bayesian optimization algorithm that someone's just published in Science, whatever, this isn't something that we could use here. And you could. That code is open source. You could do that tomorrow. But that sort of rank of people that are not used to doing things in that way, and are probably sort of like, yeah, culturally quite almost threatened, or just don't understand it. But in our case, I guess one thing we're doing is almost just having these agents to change, in that we have trained the PhD students in all of this from the beginning. So they're just joining those groups already with the mindset they use Python, they can see that they can use it. So I hope we're quite close to a tipping point in which some of these other groups, even not with having to very much work with a specialist, could start to use these things more. And I think it is going to gather a lot of momentum quite quickly that way.
Very good, thank you. So thanks a lot for agreeing to be on the panel. This concludes the first panel we have. So let's all thank our panel members. And we're moving on in the program with our next inviter talk. Do we have the speaker?
Okay, so our next speaker is Amer Hossein Nagdi Dorabati. So